But let's go back and read the definition. A critical value of a function f is any number c in the domain of f for which the tangent line is horizontal or for which the derivative does not exist. So a tangent horizontal line, notice looking at some of these examples, like this point on the curve, if we were to find the tangent line, notice it would bounce right on top. The tip top, this is something we talked about back in chapter 1, but when a tangent line has slope 0, it is flat. That is always where critical value occurs. Another instance of a flat critical value would be right here. Technically, every point along the constant interval is critical because produces a horizontal tangent line as well. So you could actually say it's critical on this entire interval. Again, this is not something that is very common in normal mathematical functions. And also, notice another thing it says is when the tangent line is either horizontal or for which the derivative does not exist. And remember, cusps and corners and things where it rapidly changes slope, these are points where the derivative is undefined, because if we were to look at the limit of the slope in each direction, those limits would not agree because those slopes are different, meaning that the derivative is undefined. Because on these sorts of points, we can't actually figure out the slope, because the slope, there is no such thing as a slope at a point when it changes instantaneously from one part to another. So I'll go ahead and circle those in red, but we'd say that the function is not differentiable at these points, or the derivative does not exist at any of those 4 points. But those would all indicate critical values as well. So what's easiest to remember is if f prime of c is 0, the derivative will not exist, or if f prime of c does not exist, then sorry, I said that wrong. If the derivative is equal to 0, it will indicate a critical value, or if the derivative does not exist, it will indicate a critical value. And our book uses c to indicate a critical value. So you could either use c or x. I've been using x to denote those, but you can also just say c is equal to. That's perfectly fine. So let's look at example number 4. It says find the critical values in the following polynomial functions. So let's go ahead and do it. So we could always start by taking the derivative and setting it equal to 0. Very similar to what I did above. So g prime of x equal to 0. I don't know why this is in red. Change that. But actually, I want to first know what is the actual derivative. So the derivative of g prime would be, well, derivative of x squared is 2x, derivative of 6x is just 6, and derivative of a constant is 0. And then if I take that and set that equal to 0, this is how I find the critical values. And this is a pretty simple equation. I could subtract 6 from both sides and divide by 2. But what I would get is x is equal to -3. And again, I could say c is equal to -3, or just leave it as x equal to 3. But this would indicate that this function has a single critical value. And if you actually look at the graph of this, it's a quadratic, which, as you probably remember from algebra, means it's a parabola. But it will have a graph that looks something like this, and it will have a point on it at -3 where it's changing from increasing to decreasing. And doing one more example, let's say we wanted to know where the critical values are for h. Again, same deal. We could start by taking the derivative of h prime of x. So here, I could start by expanding this out first, or I could use the chain rule, because here I could take the derivative of this whole thing by just applying the power rule, 3x minus 1 squared. But I can't forget that I need to take the derivative of the inside. But in this particular function, the inside, the derivative of x is just 1, and derivative of -1 is 0. So this would actually just be multiplied by 1 by the chain rule. Let me rewrite this. Sorry, my dog is barking at, I don't know if you can hear him, but he's barking at something in the park. I'll go check on him in a minute. And then also the derivative of 2 is 0, so we'll just exclude that. And multiplying by 1 does nothing, so I'll leave that alone as well. But essentially what I get is the derivative is equal to this. And again, if I set this equal to 0, this will help me figure out where are the critical values. And dividing by 3 would leave me with x minus 1 squared is equal to 0. And basically this is just a repeated factor, meaning that if x is equal to 1, this will be 0. Again, I can take the square root of 0, which is 0, add 1 to both sides to figure this out. But this would indicate my critical value for this curve which again you could look at the graph to find by looking for these sorts of points.